Relays are in a ton of applications. Most notably, they're in cars, but they're in generators, they're in high current applications, they're in vehicles. Typically anything that has a AC or a DC motor, you're going to find a relay with. This one here is a rather large one, and large I mean relative to what most vehicles use. It's a 4-prong relay. This one here, we have 2 types of connectors. This one activates the relay, creates the magnetic field that closes a lever, which then completes the circuit for both of these guys. This on the bottom is filled with epoxy. So this prevents the insides from being exposed to contaminants such as air, water, corrosion, rust, engine oil, engine heat, anything like that, which means that these guys last longer and have a better shelf life, in addition to just a more predictable operating environment. Along with these type of relays, we may see in a vehicle these kind. Now the main differences between both of these relays are 2 things. One, this one's replaceable. As you can see by the contact leads, they can slide in and out of a housing. This one is designed for a through hole, designed to generally be put on a circuit board, and then it's soldered on the bottom. And the size. The size really relates to how much current both of these can conduct. When that circuit is closed, this one clearly, because of how large not just the contacts are, but the contact inside, this one clearly can connect much larger, maybe 15 or 20 amps, whereas this little guy over here may only be able to handle 5 to 10 amps at most. One last thing is you may see that some have 4 connections, while this one has 5, some of them has 6 or 7. I'll explain that in more detail a little bit later, and I'll make sure to be as clear as I can with why that is. Before I move on, there's another type, right? So if we have field replaceable, these ones are not so field replaceable. They're through hole designed to be on a system board, such as a system board like a circuit board. And of course we also have these guys right here, and this is what's referred to as an SMD, because this one actually is mounted right on the system board. This one's a good example of what's inside, because clearly this is a bad example. We have over here your standard 5-pin. I say standard because they're typically 4 or 5-pin. And what we can do for clarification is really just remove this cover off, which is very nice. And now we can see the operation of how this works. I'll give an example later, a live example of this in action, and explain the difference. But I do want to show this close up because I found this actually at the tail end of my video. So now it's going to be put in front. Because this has 5 leads, I'll point this out and it'll make sense later. You can see that you've got one lead coming up here that's on the top, and another lead on the bottom here. And this guy right here is what connects the 2 wires. So it's either current is either going to go through this one in the resting. When this is energized, the magnet is going to energize the piece of metal, turn it into a magnet, and click, it's going to hit down. When it pulls it down, now this one is energized and this one is de-energized. So depending on the position of this guy right here is going to determine where the current flows through. And as you can see, you could have the current ready to flow at any moment here. This is the supply. And these 2, depending on what state it is, which one receives the current. For example, during the daytime, it would be turned off for the most part, so maybe this would be your daytime running lights. At nighttime, a sensor says, hey, it's dark out. It activates the solenoid. Now all of a sudden power flows not from here to here, but it activates this guy, and now power flows right from here to here. Now we have the nighttime running lights. The switching is controlled by magnetism, concentric wire that's laminated so it doesn't conduct side to side here, induce magnetism within a solid steel or metal core, and as a result of that, create the magnetism. Those 2 wires are controlled by here and here. So when these two are energized, it pulls this guy down, and that's where the switch comes. So for those of you who want to know the basics of what exactly this does, what is the object of this relay, let's start kind of at the fundamentals with a good quick example. I apologize ahead of time for my horrible drawing skills. Imagine for a moment that you're in a home and you're relaxing, maybe watching TV, maybe reading a book. And you are up on the second floor, and before you know it, all of a sudden the power, or maybe you've got a wall-mounted TV here, goes off. So you have no more power. First thing you're going to do is see if it's your home or the neighborhood. You figure out that it's your home, doesn't matter. So you go all the way downstairs into the basement. Here you are in the basement with a nice flashlight trying to figure out which way you're headed to. And what are you looking for specifically? You're looking for this box right here, right? This is where the power is kept in the circuit breaker box. So you go to the circuit breaker box, and inside the circuit breaker box you say, okay, which one do I need to flip? And you say, okay, this one's over here, and the rest of them are all on one side. So you go through one by one and you flip it to the correct side. All of a sudden the power is restored. Yay. So why is this drawing pertinent to what I'm referring to? Well, think of it this way. Humans do operate on very low voltage, right? But the house, right, the TV, the electricity, the cable, the refrigerator, all of this equipment runs on amperage, right? The toaster alone is 15 amps. Clearly, if 15 amps went through a human being, it would die. So the human in this case can be thought of as kind of a physical interpretation of someone carrying the load. We operate on a very small load, but we're able to switch on high voltage, high current applications and devices. That is precisely what this guy right here is. We can control with a small amount of amperage, with a small amount of voltage, we can control a ghastly amount of amperage. In fact, something like this can typically handle 15 to 20 amps. But as we'll see in a moment, the operation doesn't even take anything close to that. I'm going to use this whole roll. And I'll show you why we can do that. If you take a look, for the most part, what do we have? We have concentric windings wrapped back and forth around a central disc. Now you can see I have nothing in here right now. I'll put a piece of metal in there a little bit later. But look, I have one connection here and I've got one here. So easy enough, I should be able to, if this is correct, apply a voltage, put a solid piece of metal in here, and I should be able to show that it actually does create a magnetic field within the rod, and I should be able to pick metal things up. Why am I showing you this? Keep in mind that when we take a look at this guy right here, we're seeing the same property. See? Yes, these are smaller wires, and because they are thin, we can have more density of these wires running around the solid piece of metal, which would create a stronger magnet. Now what's really interesting about something like this is, just like this wire over here, this wire actually has a lacquer coating on it, which means that none of these wires next to each other are touching. They have a thin, you can think of it as a plastic coating, like a paint coating, around the entire wire except for the very end right here. That means that while none of these are touching, it acts as if this was one long wire, just like this, just a thicker coat. And I mention that just so someone's not saying, well, you know, aren't these all connecting? Isn't just one big wire? So right now, for this particular load, we have at 1 amp at 1.43 volts. What's interesting, when I connect these, you will see that amperage lower considerably, all because of the diameter of the wire. At any rate, let's take a look. So I have current running through this wire, just like within the inductor, that's part of the relay, and we have a solid piece. Now this is just a standard screwdriver, and it's not going to be a strong magnet, because there's a lot of variability in distance, and this makes a big difference in how it works. But let's just see if I can pick anything up. So fairly weak, but as you can see that I'm able to pick up small pieces of metal. Okay, so this relay is now connected to the power supply. I'm going to turn it on. Okay, and I'm slowly going to raise the voltage, and let's see if we see any movement. Oh, there it is. So at 4 volts, that's when this becomes operational. And hopefully you can see that clear. What is happening is I'm going back and forth, increasing and decreasing the voltage. I'll try and zoom out a little bit here. And what is happening is I increase that voltage, is the magnetic field becomes strong enough to push that lever down, that spring-loaded lever down. When it's weak enough, it loses the magnetic effect and the spring goes back up. When it connects initially, you can hear that. That's when that current would flow. That's when this side here and this side over here, these two wires connect. So what I have here is the power supply with 0 voltage and 0 amperage. It is connected to this relay, which is hot right now. And I say that it's hot because I've got power, 120 volt, 60 hertz, up to 15 amps available as soon as this relay closes. So I've got one, let's just imagine the positive wire going straight to a connection on this fan. Now the other wire, which is this exterior one right here, that is going through this black cable, and it is all the way on this end right here. Now, as discussed previously, because this relay is not activated, we should not have any power flowing through. This red one right here is what travels all the way back to the fan. So when this guy closes, what should happen is power should flow, if this works, from this lead up across down this metal and then right back to the fan, completing the switch, which means we'll have a small current, these two, from the power supply, inducing a magnetic field and then creating a magnet within this coil enough to push this down and allowing electrons to flow from one wire to the other, because these will be connected. So let's see if I do that. And on the with my right hand, I'm going to increase the voltage, and you should see that the fan to the left hand side should turn on. I'm at 3 volts. Oh, there we go. So perhaps you can see how the fan turns on when that voltage goes up and this guy closes. So we have 125 volt fan whirling around, and it is being controlled by this very small but clearly very well designed relay. Now, as I mentioned before, this fan may be using a lot of current, and it's 125 volts, but the switch is being controlled by none other than a standard 5 volt and 61 milliamps. That is a switch that could very easily be controlled by any number of system boards. Cars are a great example where we have small electronics controlling large applications. You can find them in the steering, to turn on the flashing lights, the fog lamps, the doors, to move the seat forward, back, up, down. All of those require an AC motor or a DC motor, depending on how they're designed. The lights. they're generally 10 to 15 amps. Could be more, could be less, I don't know. It just depends on the model. But the point is, these relays can control high current applications. This is an interesting diagram of the actual relays, and what you can gain from a graph like this is you can have one relay built in. Maybe when that is actuated and that circuit is closed, two switches turn on, not just one, hence the twin. You have silent ones. If these guys right here, for example, are very close to the driver's side, you may not want them hearing that click, click, click. So these ones are designed to be silent. These ones here are designed to be extra small. You have SMD over here that sit right on top of the system board, whereas some of these, like this one right here, these are through hole, while these ones here actually rest and can be pulled out at any time and replaced in case they go bad. As you can see, different sizes, different applications. Clearly these are going to be higher capacities. We saw these leads are considerably larger.